Okay, let me see here. So at some point, I will have to give you guys a project, which will be more interesting. Maybe you can do in groups. I know you are busy with research and classes, but I think if you do in groups, you can reduce the amount of time you spend on it. But at the same time, you learn a lot because I will plan to design the exercise to be a little bit involved in case that, somehow to use concept beyond what we are discussing here. So what do you think about that idea?
It sounds good.
I think it's good.
Yeah. All right. We can proceed. Let me see here. What am I doing? Oh, okay. So last time we talked about binary logistic regression, and we tried to fit and calibrate the true value, like simulated data where we know the true coefficients, and then we try to replicate them. And what we did is modifying the algorithm that we had on linear model by substituting the loss function for logistic regression, substituting the prediction function for replacing the prediction function for logistic. And I think for the most part of the code, we left it uniform. So, or similar to what we had in the linear regression. I think it's right here, right? So we know that in linear regression, we have y is equal to mx plus c, and the loss function is very easy, y minus y predicted bracket square. You add all of them together, and you divide by the number of row you have on a data set. So in in the logistic regression, we looked at the mathematical formulation and how the loss function come about. And then we say that, we can either use sigmoid, which is logistic, or we can use normal distribution, particularly cumulative, right? Because it gives us the same S function as logistic. I wanted to talk about this. So on this part here, we replaced we replaced this linear function by logistic, which is the sigmoid. And then for mean square error, we replaced it by the binary loss function, okay? And then we trained the algorithm, right? We left the part of optimization the same as the linear regression. And then we calibrated the function, okay? So today we gonna look at multiclass regression, and the multiclass is coming from the fact that you may have data that has an outcome greater than 2, right? And a good example here I provided last time, you are trying to classify, let's say, fruits, animal, and cars, or you may be trying to classify injury, maybe non-injury, and fatal crashes. So meaning you have 3 groups. And you can have even more than 3, right? Maybe 5 group or 5 or 6 group and so on. And once you have that problem, then that become what we call a multi-class regression. So the multi-class regression, the formulation, right? The mathematical formulation is similar to logistic regression or binary logistic regression. So what did we say about binary? So the binary logistic regression has a Bernoulli distribution as the probability function defining the characteristics of the outcome. And the outcome here is only 2, right? 0 and 1. So we said here the outcome could be 0 or 1. And we say that Bernoulli distribution receive probability, and probability here we estimated using sigmoid. So this is what we call sigmoid or logistic function. They are the same. And then we say that this parameter here, the prediction, the bx is equal to b naught plus b1 times x1, b2, x2 plus dash dash, right? Whatever number of attribute you have. And then we say that if you take, I think we derived this equation, you can make the subject, what is it? We can make the subject log of p over 1 over p, and you end up with something like this, right? Which we say this one here, log of p over 1 over p, this is logit. And this logit is equivalent to the linear combination, right? Summation of your attribute and coefficient, okay? So the same thing, multiclass regression, or sometimes you can say multiclass logistic regression has Y randomly distributed. So here, instead of having Bernoulli, we have what we call categorical. Okay. And in some books, this categorical distribution is the same as multinomial distribution. And usually the categorical is defined by P. Okay. P is probability. And probability here are estimated using what we call softmax. Okay, and here will be the softmax of the B times X, which I will explain later, right? And then the BX here will be the same as what we have seen before. Here will be B naught, B1, X1, plus B2, X2. So I'm going to introduce some coefficients here. And we'll say here is BJ, okay, BJ times X. And maybe here we can say this is XI. And again, I'm introducing these letters. XI representing you have X1, X2, X3 as your attribute. And BJ here, you have B1. Maybe I will explain later. So this will be BJI. So you have B1, 1, you have B1, 2, you have B1, 3, you have B2, 1, B 2, 2, and dash dash, right? So why do we have that? Because in multiclass regression, we know for sure that we have more than 2 outcomes or group. So, and therefore, in the regression that we are fitting, we have a regression coefficient that is fitting the first class on your response group. And then the second one here will be representing the second group of your response class, and so on and so on, okay? So I'll come here, I'll write BX, B naught, B1. So just for clarification on the Y, let's say in our regression, we have 0, 1, and 2. And those 0, 1, and 2, if you are dealing with crashes, think about it. This could be non-injury. This could be severe injury. This could be fatal, okay? And if you are dealing with classification of vehicles, this could be passenger car. This could be maybe SUV or minivan or buses. And then this one could be trucks, okay? So hold on, let me. All right. So those could be the classification or groups that we are dealing with. So in that case, in our linear regression here, this B, we can say this is BX for the 0, which is class 0, which is if we are dealing with car classification, that will be passenger car. And then we'll have BX for 1. So which will be here, B0 as well, B1X1, here will be B2X2. So just to make sure that we have different coefficients, I'm going to introduce here, this will be 0, 0, 0, meaning B00, B01, B02, okay? And this is representing the 0 there, okay? And then for the next one, here, we have B10, B11, B12, and then of course, for the last group, you have BX, this is for 2, this will be B 20, B21, X, and then B22, X2, okay? So all of these, they are representing what I wrote area there, which is BJIXI, okay? And then, how does the softmax look? The softmax look like is a function that will give us probability, because fitting this regression here, what will happen if you have the coefficient negative, maybe negative here, you may have negative there, so the summation will be negative. And here maybe positive, negative, positive, negative. In the end, you want to change that estimate into probability. And probabilities here is you want to have a softmax that is going to change those estimates into probabilities, and the probabilities are the ones that are going into categorical, okay? So how do we get that? We just needed to have a function that is normalizing the estimate. And that function is, if you have softmax, I think let me write here of you have softmax of Bx. This will be equal to exponent of B of X, okay? And then you are dividing by summation of exponent of B of X. And here you are starting from, we said J is starting from maybe whatever attribute you have here. So 0, right? So you have 0, and they're going all the way to K. And the K here will be the number of groups you have, okay? And if you look at this model or function, you are just normalizing. And normalizing, you are trying to make an output that will guarantee you to be ranging from 0 and 1, right? It's like you are taking, think of it, you have 0, 1, 2, 3. Now you are computing 1 over the total sum, right, of 1, 2, 3, right? And then 2 over the total sum, 3 over total sum. So whatever you have there is going to be a number that is ranging from 0 to 1, right? And if you are adding those normalized output across the group, right, in each group, they should add it to 1 because of the function that you have. Okay? Any question?
Dr. Emmanuel.
Yeah.
Yeah, so I want to find out the reason why we are using exponential function for the softmax. So if the motivation is trying to normalize and get the outputs between the range of 0 and 1, then can't we just do the number divided by the total? So why the need for us to use the exponential, please?
Because the exponent, I think they start from 0 to positive infinity. Do we have any negative? Probably not. So if you do that, what you are suggesting, Steve, you can get a negative. Think about this coefficient here. The summation here is negative. This is negative. This is negative. Whatever here is going to come out is negative. So if you are doing the normalization, you have negative 20 divide, let's say here the summation is negative 20. The summation here maybe is 10. The summation here maybe is 5. What will happen is you have negative 20 divided by 20 negative plus 10 plus 5. The output here will be negative something. So it's not going to be a probability. So the exponent here is guaranteeing us that even if you have a negative like negative 20, if you substitute negative 20 here, the output will be a positive value. And the sum here will be always a positive value. So whatever you get here, yes, is the number that is ranging between 0 and 1, and there will be probability. Here, yes, it's going to range between, it may not range between 0 and 1, probably will range between negative 1 and 1 positive. You get it? If you go without putting exponent, your output will range between negative 1 and positive 1. You put exponent, your output will range between 0 and positive 1.
Okay,
Does
yeah,
it make sense?
that makes sense. So what if you decide to just square the numbers? Will it make any difference?
Square the numbers. I have never tried that. What will happen there? Yes, you get a positive value, but what is gonna happen? Are you gonna get 0 and 1?
That would be
Yes.
the other question to
Yes,
satisfy.
you get 0 and 1. I mean, the interval to be 0 and 1. I have never thought about that. Maybe something that we can experiment it and see.
Sounds good.
Yeah, but I think why we don't use that because of the loss function. You come back and see the loss function work perfect with this softmax regression, this softmax transformation function. So if you have, if you square those coefficients, most likely you have to look for the loss function that will be compatible with that. I think that would be my quickest thought in your question.
Sure.
Any other question? Okay, so now this become the mathematical foundation for multiclass that we're gonna use. Okay, so the key thing here to know, if you have 3 classes that you are trying to classify, it means you have 3 different regression fitting those classes. You have 4 classes, 4 different regression will come out. You have 5 different regression. You have 6 different regression will come out. Okay. So, however, though, you see in the literature, some of the multiclass, you can use one of the group as what? As a comparison group. And then if you have one group like 0 as a comparison group, then you are output will be only the two regression. Okay, it will be this and that. If you have 5 and then you are using 1 as a comparison group, then that becomes the regression that you fit. Out of 5, you have only 4. Okay, so the key here, what I'm trying to say, you see multi-class regression or discussion out there. They are fitting 3 category, but the output they're calibrating is only, the calibration output is only 2 regression. If you see such a model, just know that they are using one of the group as a comparison group, okay? But for me, I'm focusing on the machine learning aspect of it, and machine learning aspect of it, all of the regression, multi-class regression, when they fit them, they tend to have, the regression fitted will be the same as the number of group that you are using, okay? So if you are interested to fit the comparison, I can show you later or maybe in the future. It's just a modification on how you plug in the Softmax, okay? And then you make sure that one group is the comparison of the rest, okay? So, but for this class or this discussion, let's focus on machine learning aspect, which if you have 1, 2, 3 group, you are classifying, then the outcome will be, the fitted regression will be 3, okay? All right, so the loss function. So the loss function in the, any question?
Yes, Dragidando, I have a question there. Sorry. Yeah. Regarding the having one category as a fixed or as a reference, the point you just talked about, I had a question out of curiosity. I just read a paper last week. They were fitting something without the comparison. So it's like in the language, when you have something like in a comparison, let's say you have 2 levels, zeros and ones. So the interpretation will be like compared to the reference which is in 0, 1 maybe it's highly or lower compared to the reference. My question is, when you have 2 different models, like you don't fit the 0 as a reference, you have 2 separate, will you still have the language of comparison because of this? There are 2 different regressions, like one is not a base of the other. Will you also say one compared to, like, I don't know if you're making sense out of that question.
No, you're making sense. I understand where you are heading. Yes, you can do comparison. What will happen is, you have probabilities. So here, if you have 3 classes, you have 0, 1, 2, and then you have a probability. A good example here will be 0.3. Here will be maybe 0.1, this 0.4, then here you have 0.6, okay?
Yes.
So think about this will be row number 1, row number 2 will be maybe 0.6. Here will be 0. Maybe 1, 0.3. So yes, the comparison here will be based on this, and that. Okay, so you can say 1 class 1 compared it to 0, this is what is happening, and 1 compared it to 2, this is what is happening, or 0 and 2, this and that. You can do comparison. But on your end, what you are talking about, you have 0 as a base group, and then 1, maybe, and 2. Here you have a probability 0. In fact, we don't estimate probability. We estimate odd ratio when you have this.
Yeah.
When you have this, this will be more of odd ratio, not here will be odd ratio. And odd ratio will be the same as P over 1 minus P. And here will be P over 1 over P. And then you compare this odd ratio with reference to 0. Yes, the language, how you put it, is going to be different. because when you have a comparison, you'll be saying, oh, as compared to 0 as a base group, this is what happened on category number 2.
Yes.
Or as compared to 0, this is what happened on category number 1.
Oh, yes.
But when you are dealing with, and your explanation will be more on odd ratio. But on the other hand, this part here, you are not going to say, oh, as compared to 0. Yes, you can do as compared to 0, but your bases should be based on the estimated probability that you have.
Okay.
Or the statement will be different.
Okay.
Yeah.
Thank you.
So we'll discuss more when it comes to interpretation, because in machine learning, you can compute the odd ratio, but in most cases, we go with sensitivity analysis. And sensitivity analysis, think of it like you are plotting a graph that is representing probability for class 0, probability for class 1, probability for class 2. I think I wrote a paper before. I want to show you those graphs. So which paper is that? Anybody read my published paper that I'm dealing with Multiclass? Oh, where is it? Yeah, give me 1 minute. I think I can find it. Yeah, so I can plot it, because finding it, maybe after the seminar, because we don't have enough time. After seminar, I will look at it and share with you. But what will happen is, let me plot it here so that you can see what will happen. So what will happen is, we normally plot a sensitivity kind of analysis graph, which will be, think about, you have this, right? This could be AAADT, and you are plotting against the probability of injuries. Okay, this is P, and they sum this to 100, right? So let me say right here 100. Okay, so let's say you have, if you have two, I think for you guys to understand, if you have two groups, okay, let's say group 1 is what? Is injury, and then group 2 is what? Is non-injury. What will be the graph? The graph will be something, it depends on the relationship. If it's non-linear, let's say parabolic, you have a graph which is something like that. Okay? And the other one will be something like this. Okay? Meaning, if you are dealing with this as injury, right? And if you are dealing this with non-injury. Again, this is just an example. So what will happen is, at any point on a graph, the summation of probability should be equal to 1. Why? Because you are dealing with two outcomes. So if this point here is 100, as an example, this point is 100, then this part here should be 0, right? Because if we take this non-injury, and the injury should be 1. If this part here is 0.8, then this part here, if I draw a line vertically, this point here should be 0.2, okay? We agree that. And this point here where they are crossing, they should be 0.5, 0.5, right? Why? Because if I'm adding them, they should add at any point on a graph, they should add it to 1. Here, maybe this is 0.8. The part here should be equal to 0.2. So you get that, right? So now when you have 3 class, The concept there will be the same. That the sum of probability should be equal to 1. But now here we have how many? We have 3 classes. So you may have maybe a function which is going like that, maybe another function, again, it's just an example, going like that. And then another function will be going maybe like that, okay? The key here is if I take the probability here and there, this may be 0.8, they should add to 1. So this could be 0. Again, this is an example, maybe 1. This should be, so maybe this should be what? Because they should add it to 1. This 0.8 is 0.8. So maybe 0.01. Maybe this should be 0. Something like that. Okay? And if you're looking at this point and that point and that point, they should also add it to 100 or maybe 1%. I think this is not right, not 100. This should be 1 if I'm dealing with decimal. Okay, and the same here. Okay, so that's how we plot a sensitivity graph. So you find in most cases, we tend to look at a sensitivity, a graph that is plotting a sensitivity analysis of an attribute. And then you try to look at a given point, what are the probability look like for the 0 class, 1 class, and 2 class. And then you write your discussion based on that. Okay. Any question?
Is there a difference between the softmax function and the logistic function?
There is. Logistic function is equal to what? Is 1 over 1 plus e negative of what? Bx. Or this should be, if you write, this will be, you see also in the literature people are writing e b of x over 1 plus e b of x. So that should be the same. Now, softmax is different. Softmax is e of b of x over summation. Here is summation of e b of x, depending on how many group you have. So group 0 to k, right? So meaning if you extend this, this will be e b of that over e b1x1 plus e b2x2 plus e bx3, 3, right? This provided you have, this is j to k, you are talking about when k is equal to 3, okay? So if you look at it, this function here and that function there is not the same.
Okay. Yeah, thank you.
All right, any other question? All right, the next thing here is to look at the loss function. And the loss function here is, let me see here. So I'll go back here. So what did we say? For us to fit a machine learning algorithm, we needed to have a prediction function. we need to have a loss function and steps, right? Optimization step. So far, we have seen the prediction function. Now we just needed to go look at what? At the loss function. So the loss function in categorical or multiclass, we normally use what we call a cross entropy. And the cross entropy is something like loss is equal to y times log of the bx. So here I'll write that and xi, right? So as long as you know your y and then you know the log of this, then you can go ahead and compute the what? You can go ahead and compute the loss, okay? So now I'll come back here and say, for Softmax, we need the prediction function. And the prediction function is gonna come from here, right? We have P, we'll compute P, Softmax of this, and then we have the extension of BJX, XI in this format, right? And then we'll be able to predict. So if we want to write here, we'll say P will be equal to soft max of Bij of Xi. And then here we know that the B, let's say if we are dealing with group 1, this will be B1 J Xi. This will be equal to B1 0 plus B1 X. So this will be 1 1. This will be X1 plus B1 2 X2 and so on, right? And then if you are dealing with B2J Xi, this will be B20 plus B1. So this will be 2 1 X1 plus B22 X2 dash dash, right? And then if you are dealing with 3 group, so this will be JX. So this will be B3 0 plus B3 1 X1 plus B3 2 X2, right? And then remember, here we'll have probability. So if we want to get the Y predicted, we need to change the probability by saying what? You look for max of P, right? Whatever maximum probability predicted will give us the Y, okay? And now the loss function, we have to use the entropy, cross entropy. The entropy here is what? We say it is Y. This will be log of B I J X I, okay? So one thing that you needed to know here is, remember the Y predicted here will be in form of 0, maybe 1 and 2. You want to change, okay, I'll come back. What happened here? So it'll be 0, 1, and 2. And this one here, if you look at it, if you have how many group? You have 3 group. It means your data set here will be n number of row, comma, k, n being number of row on your data set, k here being the number of groups, right? I'll write here of group. Okay? But y, if you look at it, this y will be 0, 1, and 2, which will be, if you look at this will be n, right? Meaning number of row. You have 0, 1, 2, all the way to the total number of row you have on your data set. And if you come back and look at this, it's not going to be able to do it, to do the multiplication, because you are dealing with the number of row, which is whatever number you have at your data set, maybe 100. Here you have n times k, number of row will be here maybe 100, and k here you have 3 groups. So you can't multiply that. So you needed to transform the data to make sure that you are able to multiply. And how do you do that? Usually in Multiclass, we transform this by what we call a one-hot encode. A one-hot encode is you are creating a matrix that will be the same number of column as the number of unique group you have on your data set, which will be, you want to make sure it has number of row and you have the number of group, right? So meaning your data will have n comma k as well. And how do you do this? To do that is, if you have your data set as an example, let's say your column of y is 1, 0, maybe 1, and then 2, and so on and so on. So you want to transform the y into 3 matrix, meaning you have 0 and 1. So meaning for this part, you have 1, right? And you have 0 and 3. So it means at a position of 0, at this point, this row will be 0. At the position of 1, you have a value which is 1. And then at the position of 2 on this is 0. So you have something like that. Here you have 1 at the position of 0, you have 1. At the position of 1, you have 0. At the position of 0, at the position of 2, you have 0. So that will be your matrix. Coming here, at the position of 0, you have 0. At the position of 1 is 1. And at the position of 2, you have 0. Okay? Coming to 2 here, the position of 0 is 0, position of 1 is 0, position of 2, you have 1. So this transformation of data is what we call one-hot encode. And if you look at it, this will have number of column, 1, 2, 3, and the number of row will be equivalent to the number of data set, which will be n comma k. And if you have n comma k and this part here is n comma k, you'll be able to multiply. So that's what we call a one-hot encode. Okay? Any question?
Yeah, Dr. Emmanuel.
Yeah.
Yeah, so just a quick one. I think the expansion above, where you were trying to expand BIJXI, I think that expansion is valid for BIJXJ, the way you've done the expansion.
The expansion is valid for
BIJXJ.
BIJ. Let me write here. So you're saying BIJ
BIJXJ.
XJ.
Yes, sir.
And then the no. Okay, you are right. So I think we needed to switch something, but what we need to switch here is this one here. Instead of BI, this will be K. And I'll explain to you why. So this will be BKJ. And the XI here, because you have, actually this will be, they always confuse me. They also confuse me. So but I understand the expansion of it. So this will be J K, okay? J representing the number of group you have, K representing the number of attributes, okay? And then X here will be IK, meaning X, you have number of rows, which is 100, and K, you have different number of attributes, okay?
All right.
Yeah, and here we can come back and write, this will be 1K, and here will be the what? The IK. Here, if you look at the expansion, we said B of 1, 0, 0 representing the K, how many attributes you have. Here now we are switching B of 1, like attribute number 1 for the X1. And then you have this part here for B for 2, and then the X2. The same here, this will be K, and this will be IK, and then this will be K, this will be for what? For IK. So if we want to define those, I'll write J representing the number of class in your response value. And then if we are looking for K, this will be the number of what? The number of attribute or independent variable in your data set. And then for the, what do we have again? I, this will be the number of your sample size. That clear, right? That's clear our doubts now.
Yeah, sure.
Okay. Yeah, they always confuse me as well, but I know what I have to write, especially when I'm writing the mathematical formula in the code. So meaning you have, because you have variation in number of classes, you have variation in number of attribute, and then you have variation in number of rows of data set you're dealing with. Okay. Any question? I think the next thing here is to encode this, what we just discussed here. So what I will do, I will switch my screen and go back to Python. Let me go back here. So what I will do is I will start simple and then we'll keep expanding it. So I'll come here. Copy this. And this one here. Right. You can see my screen, right?
Yes, please.
All right, so what I need to do here is to create a column, and this is what we have. So the first thing that I want to show you, so I'll write here the name. This will be, okay. I'll write 05. Okay, so the first thing that I want to show you is changing this kind of class into a matrix, which look like this, which we use in what we call one hot encode. And so how do we do that? I will start importing JAX and then import JAX dot numpy as J and P. Right, for now, that's what I'll start with. And then let's say we have data Y, which has what? Which has J and P dot array of, that's 0, maybe 2, maybe 0 there, maybe 1, maybe 3, okay? And we want to create a 3 matrix using one hot encode, a matrix, because here we have only 0, 1, 2, and 3. So I'll put this one as 0. Okay. So we want to do a one hot encode and produce the n times k matrix that is following this nature. Okay. And the way to do this is in Python, we have a function that is called I. And the I, so I'll run it here. If you write J and P dot I, let me say I want to create a matrix with 2. You see what is happening? It's creating what? For you guys in mathematics, what kind of matrix is this? The one that has 1 on a diagonal line. What is it? Identity matrix, right? Yeah. So now let me create 3 here. You see what is happening? So it's creating an identity matrix with 1 along a diagonal line, okay? So what if I do this and multiplying with Y? What is gonna happen? So it's gonna happen, what is gonna happen is going to multiply on the value that, so let me go ahead here. So we have how many unique values? 1, 2, 3, right? So 3 is fine. So now I will go ahead and multiply this. Not to multiply, if I add Y here. What is happening? I didn't run this. You see what is happening? So after doing this operation, you see that 1 is located on a position of 1 in my matrix. So that's why it's substituting 1 there. Everywhere else is 0. And then here you can see is number 2. At a position of 2 is substituting 1. Everywhere else is what? Is 0. And then we have 0 is substituting 0. All other point is what? Is 0. And then here is substituting 1 because we have 1. And here substituting 1 on 0, the rest is 0. Okay, so that's how we can achieve the one hot encode, right? So that's the first part. The second part is for us to be able to estimate the softmax. The softmax will write a function df softmax of here I will just write bx, let me say a, and what will happen here will be the numerator, what did we say, is exponent. We have to say jnp dot exponent. Where is it? I didn't write here. So, but you all remember from this slide. From this slide here. Here. The softmax is EBX summation of BX, okay? So this will be JNP of A, okay? And then you are dividing by what? Sum. So we can do JNP dot sum. JNP dot sum bracket of JNP dot exponent of what? Of A. Okay? And then this will be the return. Okay? So let me show you what is happening. So let's say we have the matrix. So let's say A is JNP dot array of a matrix which has maybe -1, maybe 1, -4, and then 0. Okay? And then the next row is what? Give me a number, any number here. I just want the one that has negative, some of it positive. Give me any number. Maybe 3, negative what? 4.5, and then 6, maybe 8, right? Let me go ahead. What happened here? Did I miss anything? Did I forget the other square bracket? Okay, so let's go ahead and do the softmax of A. You see what is happening there? Is changing. Something is not right here. Let's see. So ideally, it should change those into probability. And each row, it should sum up to 100. But looking at it, it doesn't, right? It means whatever is coming out here is not right. We need to maintain the axis. So I'll change here and write axis 1. Let's see this. Something is not right. What did I miss here? Look like I have to add keep dimensions as a keyword. You see now? So I needed to write axis 1 and then keep the dimension. And if I take this, add them together, this should give me 1, which guarantees me that's a probability. You see? You have 1.0001 something because of approximation, right? And the same here, if I add this row, it should give me 1. Okay, you can see that. So any question about the softmax function? Any question about the softmax? So basically, just if I want to repeat this, let me go ahead and copy this actually. Copy. I'll paste it here so that we can be looking at it. So one thing that I want to explain here, think about this. You have three different what? You have three different rows. So here you have two rows, but you have three different attributes, and you want to change this into a probability. And the Softmax, you can see there, is changing those numbers into probability. And if you add those probabilities, basically we are adding them to 1. Okay, so which give us what we are talking about here. A softmax will help us to transform the data from whatever scale they are into a range of 0 and 1, right, in terms of probability. And the one thing that you can notice here is this is the negative value, right? Look at here, the probability is low. This value is the highest in the rank between these three. Here is the highest among the three. Here, the highest is 8. You can see here, the probability is higher, followed by 3, followed by that, and then the value of negative, producing a very low number, okay? So basically, that's another way of looking at it and see if the numbers, the probability are computed in the right way, okay? So now, how do you build a predictive model for multiclass, which look like this? So what we can do is we can do like what we did last time on binary. So what did we do in binary? So this was our example. So I'll copy this. And put it here. And then I'll copy this and put it there, okay? NP, okay, we need NP. Okay, so what we need is, let's say we have 3 classes, so we'll copy this. Okay, so if we have 3 classes, it means we are predicting 3 classes. It means we have 3 different equations. So I will copy this into 3 different equations. So we have 0 here, 1 and 2, okay? And then maybe this, to keep it simple, I'll just create 2 groups and then remove the said one. No, I mean, just remove the attribute number 3. And then we can change this to any number, right? So maybe 1 here, maybe 0. This could be 2. This could be 5. Maybe this is negative. This could be 1 point. And this could be 6. Maybe 2. Maybe 1. Maybe 0. And this one here could be a plus, okay? Okay, and then we need the third equation. What did I do here? I deleted one equation. This is 1, maybe 2 here. Okay. Yeah, maybe 3. Okay. So what we need here on this step is to stack all of these prediction into one what? Into one matrix. And the reason we are doing this is to produce something like this, okay? And then set it into the softmax and see the probability. So how do we put it in a matrix? You write maybe logits, or maybe we can say, yeah, logits is equal to what? J and P stack. I will just copy this. I'm lazy. And then I'll say the first part is this, the second part is that, and then you have that, okay? So here 1, this one is 2, this one is 0, logit, okay? And then let's see how logit look like. So I'll run this, run. You see? So what I'm producing here is I have these linear functions. I'm stacking them to create a matrix, and this is the matrix. And this matrix is similar to what we have A here. So we can change this estimate of linear regression into probabilities using softmax. And how do we do it? I'll go copy this and insert it here, and then change this and write softmax. Softmax, that's a function I wrote. And if I do the P here, you can all see that the probability, they are adding to 1. If I take this and that, they're adding to 1. This and that, they're adding to 1. This and that, they're adding to 1. And we can compare with logits. We say that if you have a higher number, then the probability will be high. A negative value, probability will be low. A value that is low, and also the logit will be low, okay? So meaning that this number is higher than the rest, followed by this, and followed by that. And so the probability is higher this one, followed by this, and then that at the last one, okay? So the next thing now we want to do is you can look for the max. If you look at here, we say that, I'll scroll down here. For us to get 0, 1, 2, we just need to compute the maximum value of the probability. So if you look at here, the maximum value of the probability is here. So then the estimated value is 0. This one is 0, this one is 0. So, but you want to look at the value that is what? The value, the probability where is high, you want to look at position. So if the high probability position is 0, then the estimated is 0. And when the position of high probability is at 1, then the estimated is 1. If the estimated probability, the highest probability is on 2, then the estimated value is at 2, okay? So, and in Python, the way to get that value, I think we have what we call JNP dot argument, I think we say argument max of the P. If we do that, it should retrieve the position where you have the highest probability. If it's at 0, then the estimate will be 0. If it's at 1, it will be 1. So I hope that's the right syntax. Oh no. Why is it retrieving that? Maybe we needed to give it a condition axis. Yep. If you write augmented value of P, max is retrieving, you can see, is retrieving 0, 0. So basically our model here is poorly designed. So how can we change this? So we need to change the coefficients. We need to change the coefficients. So I'm changing the coefficient because you can see the ones are here, right? Or the highest estimate is on this first equation, and it's killing everything, right? So everything predicted, the highest probability is on this particular column. So, and my suspicion is this number is too high compared to the rest. So maybe put there 0, 1. Let's see. This is much better, right? You can see this number is higher, this number is higher, this is high, this is high. So that's much better. So let's see. You can see here, and if I run, now you can see we have 0 and 2, 0 and 2. 1 is nowhere to be found, right? So we need to go back and adjust again. Adjust the, so 1 is missing because of these two negative. Maybe put plus there. That's much better, right? We have 0, 1, 2, 0, 1, 2 at least appearing, and we can even do the counts and see how the distribution they are. So, and the count here, we can do something like this. So I'll change this into Y. And if I run this and then run to see the unique value, you can see the 0 are 500, the 1 is that, and then the 2 is that. Okay, so that's a proportion of the data set. Any questions so far? Any question? So you can still use categorical distribution if you want, and the categorical basically on this stage here. So I will show you. If you want to go with categorical distribution, you just need what we did last time, something like this. And then here will be categorical. I believe that's a function. This one has to go. We have the P as probability already. P estimated with Softmax. I'm inserting them there. And then I'm generating random numbers that are following categorical distribution, which is similar to what we wrote it here. Y categorical of P and then P soft of max. The P are estimated by Softmax, and we want to retrieve the integers. So let's see what we'll get. So I'll run this. What is the problem here? Categorical. Let me run the Y. You can see the numbers are slightly different because you are generating random number here. You can see those are the estimate. And if you change the seed, even the number of estimates should change as well. So you see here, this is 358. You see now it's 384. If I change these, okay, it's changing. So basically, because we are trying to generate a random number that are following the distribution that we specify. Any question? Any question? So all the way to this step, is everything clear?
Yes. But doctor, I have a question.
Yeah.
What is the essence of keeping the axis and keeping the dimensions constant, and what are they?
Yeah, so the essence is because you are dealing with the matrix. And the matrix has different dimension.
Okay.
Oh, hold on. Let me write this. Okay, so I'll come down here. So the reason for keeping you are asking this part, right?
Yes.
Yeah, because the summation that you wanna do is the summation across the so in Python you have axis 0, 1, 2, 3, and so on, right? So I'm specifying axis 1 here, which is representing the column. 0 usually will represent the row, because when you are writing your data set, usually will be n comma k. And the n comma k, or maybe I can even run this so that you see. So let's give this as yy. And let me print out yy.shape. You see here? So yy.shape, you can see, oh, now it's retrieving the y here. Okay, so let me run this y so that we can, so this y here has how many number of rows? 1, 2, 3, 4, 5. That's why you can see here the shape is 5, representing the number of rows, and 3 is representing the number of columns. And if you look at yy, the columns are 1, 2, 3. So coming down here, we want to create a probability that is summing up across the rows. You have row 1, 2, 3, meaning you have 1, 2, 3 column. That's why I'm maintaining the axis 1 here. And why is that? Because come back to this function. We said is EBX summation of E B of X J0 to K. K representing the number of category you have. If you don't put the axis here, what will happen is he's summing probably all the rows, right?
Okay.
If I do that and ignore that, okay, delete that. And I ignore that and run this, you can see here, the probability are not adding to 1. They are adding to something else. It means it's considering all the rows. Why am I saying that? Because this is power -4, this is power -6, this is power -4. It means it's 0.0009, 0.0006, 0.000, whatever, right? So if you add those, they will never add it to 1. Coming back here, specifying axis 1, this is guaranteeing us that the summation is done across the row. Here, across the row. And the row, meaning representing each class, you can see now this is 0.7, this is 0.004, this is 0.002. If you add this, is actually giving us is equal to 1. So that's the reason why we had to go back and maintain the axis and the dimension of the data, because we want that the output to come in form of a matrix. Okay.
Oh, yes, thank you.
Any other question? All right, so this is very easy. I just wanted to show you in the prediction and looking at the matrix, right? Like you have a prediction function and you are putting them into a matrix, you are sending them into the softmax, and you are retrieving probabilities. And each probability here, if you add across the row, they should add to 1. Okay, so that's a function. And then here, we are trying to generate the sample size, following a distribution of categorical, or somebody can just go ahead and select the argument, the argument max, retrieving the position where you have the maximum probability, right? And then that's become the category that you are estimating. Okay. Now, the next thing that we want to do is this part here now. How do you calibrate? Calibration involves these three main steps: developing a prediction function, which for us is already something like this, right? The prediction will have equations, and the softmax, okay, which is something like this. And then the loss function, which we're going to write it later, which is the cross entropy, and cross entropy is the function which you have y, you are multiplying by log of your linear function. And then the y, you want to make sure that is what? Is the transformed y in form of one hot encode, okay? And then the optimization step will be the same as what we had in any other function. When we were fitting linear regression, fitting logistic regression will be the same, okay? So now, just to make sure that we are doing very fast, I'll just go ahead and edit this, right? Edit what we had on the logistic regression, and then move from there. So I would duplicate this, rename it, and write this as number 5, and this will be number 1. And then I'll open this, and I'll move it here. So this is what I'm going to edit. So what I need to do here is I'll come back here, drag this side. Right here, copy my softmax function, paste it there. And then where I was generating my data, right here, I will copy this and come back here. And then the y, which is something like this. And then I'll stack the x. And then for this example, we needed the value of x, which is something like this. I'll put it there. So this is x, this is x2 coming here. And then stacking the value of predicted, then putting a softmax. I'm changing the probability into the estimate of y. And here I needed to remove the x3 because we have x1 and x2. And then that will be x. And then, are you guys following, or I'm very fast?
We're following, but it's fast, yeah, a bit fast.
Okay, I will stop there waiting for you guys to catch up. So the first thing, you needed to have the softmax copied from a previous example, and then take the data we simulated, which is from the previous example. Now I'm estimating the value of y, and then we have the x. So if I run this, I have my value of x. And this part here, I have the value of y. Okay, so the y, which is 0, 1, 2, 3, 0, 1, 2, and then the x, I'm stacking column 1 and column 2, and of course, I'm adding a column of 1, 1, 1, representing the intercept. Okay. All right, so are you all done with that step so that we can rewrite the prediction function? Or maybe let me ask this one. Who need time for me waiting to, for you guys to catch up? Who need time? Or you are all good, I should proceed?
Yeah, we can proceed.
Okay, so the linear prediction here will be that one, but here instead of sigmoid, again, I'll go back to this part. We have this part here inserting to a softmax. So I'll go back and change this part. Instead of sigmoid, this will be the softmax. And then this part here, I will substitute the loss function cross entropy. And the cross entropy function is actually very easy. Is y times log of what? Of pi. But here we needed to change the y. If you don't change the y, you get an error because I was explaining here the dimension of this pi will be different from y. You need to transform this. And we needed to get the y 1 hot. And how do we get it? You saw last time we said the JNP dot I of what? A shape. So the shape of our attribute here is what? We have 3 unique attributes coming out, right? So 1, 2, 3. So here it should be 3. And then the y, okay? And then this y1 hot encode is the one that will come here. And the loss here, remember, you have, if you compute this part here, you have the output, which is a matrix of n times 3, right? But usually the loss output, it should be what? The output of a loss usually should be a single value, a scalar value. Either 3, 4, 3, maybe 3, maybe 4, maybe 0, and so on. So in that case, for us to be able to get that, we needed to add this and then compute the mean across the row. So add across the column and then do what? And then compute the mean across the number of rows. So what I will do here is I will do JNP.sum. What did I do here? Dot sum of loss, but this sum should be across the axis, which is 1. And then compute the mean across the row, okay? So that's a loss. So I'll change this and write cross entropy. And then this cross entropy, I will put it here. So for now, let's ignore this, right? So we have a prediction function, cross entropy coming back to the update here. And after that, now we need to come back and initialize. So in initializing the coefficient, this is going to be a little bit different. Why? Because if you come back here, we have 1, 2, 3 coefficient, and then times what? 1, 2, 3, right? Because we have 3 output, and then we have 3 coefficients. So we'll come back here. Instead of us using this, we're gonna do a random data. So we'll do JNP dot random dot normal distribution. We'll put here a key, and we'll put how many number of rows. So we have 1, 2, 3 times 1, 2, 3. So I will just write here 3, 3. Okay. So do we have the key? We needed to introduce the key here. And the key, I'll come back and copy what we had last time. Here. And again, the key here is making sure that every time we run the simulation, is retrieving the same initial value. Okay. We are fixing this so that every time we run the iteration, we are getting the same number of initial values. So now here, this will be difficult for us because we have like 9 coefficients now to deal with. And we say this we wanna ignore for now. And then this part here, I will remove all of this. I think we can get the accuracy. Let me go ahead and insert it. How do we get the accuracy? This equation will still be, the equation won't be valid. The equation here, you predict, you get probabilities. So now you want to use this equation to get the 1, 2, the 0, 1, 2. So this part here, I'll do that. Maybe I want to keep the integer. And then come back and say, whenever you have 1, 1, count it, or 0, 0, count it, or 2, 2, count it. Otherwise, ignore it. So that will work. So here, that also work. I'll take out this one. What is? I think this is good. Finger crossed. Let's see if it's gonna work. I have a problem, just random. Oh, instead of just put here, instead of J and P, put here Jax. Finger crossed. Can interpret 3. Okay. Sometimes this Jax is picky. Let me put decimal. Fraud number is not iteratable. Huh, what is this? Let me see. How did we specify last time? Oh, we don't need this. We want to put it in a bracket. That's how it's recognized. Something isn't right. The accuracy is 1. That's strange. So the loss was this 0.21. I mean 1.21, and then 0.18, 0.12, 0.0. So it was converging and then it hit something. Okay. Anyway, and are you guys following my steps? Do you need me to show you anywhere before we debug that none? So again, like what we said earlier, we just needed to insert a prediction function for multiclass, which is something like this. We need to modify the loss function for multiclass. This is the loss function for multiclass. The other part should be the same. The updating the coefficients, it should be the same because it's kind of a standard procedure, I would say. And then here we are putting 3 times 3 because we have 1, 2, 3 features, and we have classes 1, 2, 3. That's why we are doing something like that. Okay. Any question? Any questions? Any question? Let's see.
I'm getting an error.
I'm also getting an error, but yeah. Okay, so let me see first yours, and then we can come back here. What is the error? Can you scroll down? Yeah, it's the dimension issue, and the dimension issue on your dot product. Scroll up. Let me see what is the problem. 3 times 3. How about your coefficients? Your x. Let's see your x. X, there are 3. 1, 2, 3. That's good. So why are you getting an error? Scroll down. Scroll down again. Right there. Okay. 3,3. Enter. Scroll down. Everything look good. Are you all getting an error like Abdul?
Yeah, I'm also getting error, doctor.
The same error is like Abdul? Or is different?
It's different.
Okay. For you, Abdul, look okay because scroll down though, but I'm curious why you are getting 4. You see, got 4 times 3. It means it's telling you x is 4 attributes and the parameter is 3. So now the question is, you may need to check the value of x the way you are calling it, right? Because on top, oh, I see, you are using capital X, and then at the bottom you are using small letter x. Where did it go? Scroll down all the way to the step of optimization. You are using small letter x. And even on accuracy, you have to make sure it's capital letter X. So probably it's referring to what you are doing last time. What is the problem now? Yeah, you have many losses there. Remove loss in your print. Okay, that's a good start. Let's see for you, Steve. So what is the error? Let's see the error. Oh, change the J and P to JAX. J and P, remove that and write JAX. JA, yeah. Try that. What is the error now? Oh, make sure you have brackets. Those 3,3 they are in one bracket. Yep. It shouldn't take that long. Something is not right. Dynamic object. Oh, change that. What function are you using? Which loss function are you using? The problem is on a loss function. Scroll up. Scroll up. Um, Let me see again the error. Dynamic just trace an object is not callable. Okay, scroll up. Parameter XY, parameter XY. And then P prediction. And then the P. That's strange. For you, look up. Hmm. Can you put that error? You may need to, okay, you may need to check that on internet. I never encountered that before. Because everything, no, just check the one, type error dynamic tracer. Because everything look okay on my end here, I see. So why is everybody getting the same error? How about the rest in a group? Are you getting the same error or you're good?
Yeah, we are getting a different, I think. I'm missing something.
What is the issue there?
Okay, I just show this. Yeah, yeah. So it says that yeah, this one. I think it's just a
So
type.
text 2 position, but 3 were given. So your function has 2 inputs.
Yeah.
You forgot why. Oh, prediction shouldn't have that. No, don't worry about that. Yeah, you on there. Remove the Y.
Yeah, I think the rest are just fixed on it. Or not. Okay. Yeah, just start typing. Yeah, I'll just fix this. Yeah,
Okay. For you, Steve, I'm not sure what is that. That error, what it means. So anybody getting a similar error as Steve?
Excuse me, Doctor. Me, I'm getting a different error, but I think it's something wrong with just normal coding, but I'm failing to trace it.
Okay. Can we see what you have?
Yeah, I'm being told params is not defined, but I've defined it somewhere.
The initial value, where is it? It's missing the
Oh.
value.
Okay.
Yeah, so you can stop share. I'll show you how I defined the initial value.
All right.
Here. You need those lines. You got it working now?
I'm finishing up. I'm finishing up.
Okay.
Dr. Emmanuel.
Yeah.
Yeah, I think I figured it out. I was multiplying y to what we had in the bracket for the loss. Yeah, so I think I was in editing, I didn't delete one y, so it was creating that error for it. So it's running now, but the only issue is the accuracy is constant throughout all the iterations, and I'm not sure the reason why.
Yeah, the same here. You can see is 1. So I'm trying to figure out and looking at the coefficients are completely different.
Oh, okay.
From what we have. So it's the same issue. So how about you, Abdul? Are you replicating the coefficients?
So I did not print out the coefficient, but I'm getting value of accuracy diminishing.
With the
And then,
iteration.
yeah.
Okay. Anybody is getting different values?
I am getting an error, but it's telling me loss is not defined.
Okay. It means your function. You can share. It means your function isn't. You are not calling your function in the update. In the update steps. Let me see. Now let's see the error first. Oh, loss. So, and yeah, you skipped one line on your loss function, the cross entropy function. You skipped one line. So yeah, you can stop sharing. I'll show you. You skip this line here.
Okay, thank you.
All right. Okay. So now it seems like we have a problem, right? The accuracy is constant. And here we can see something updating. And we need to figure out what is the issue here. Is it this initial value as a problem? Maybe not, right? It's still constant. So is it the learning rate? Probably not. Why? Because it's updating the coefficient, but we don't see it's updating the loss, but we don't see changes there. So let me see if we remove this and then put together a few. We can see even from the beginning, the accuracy. By the way, is the accuracy function right? Prediction, probability, argument marks, axi1.
Doctor, I think I'm getting it. I don't know. I'm getting results.
Okay, let me see yours.
Yeah.
Yeah, even for you is even bad. Accuracy should not exceed 1.
Oh, okay.
Yeah, accuracy range between 0 and 100. Or 0 and 1. So yeah, that's wrong. All right. So I'll leave this to you guys to check it, right, and look online what could be the issue. So I'll try also to find the solution. Why are we getting something like that? And then I'll email to you. So what I really want you to continue doing before we meet next week, make sure you experiment more on the algorithm that we discussed. How do you fit even a linear regression? Maybe a curve that is not a linear regression is defined by polynomial function, for instance. How do you calibrate it? And then on logistic, I think there are many data out there. You can download them and fit a logistic regression and see the accuracy, right? And then for multiclass, the algorithm should be more or less the same. Look at multiclass problem and see how you can customize this function to solve that problem. Okay. So there are other things that you guys have to go look at it. For instance, Obstacks provide a built-in cross-entropy loss function. Go look at it online and substitute there. And then JAX also provide a function, a built-in function for Softmax. So instead of us using the function we wrote, can we use a built-in Softmax, right? So those are the things that you guys can experiment. Then next week, I really plan for us to start looking at neural network and optimize algorithm that maybe you have one layer of neural network, maybe two
Excuse me,
layer of neural network, and see how that works.
sir.
Okay. Yeah.
Excuse me. So
Uh,
you are saying about Optimax, Optax. What should
Octax,
we,
yeah.
what should we look into?
Go look at the loss function, the cross entropy loss function.
Oh, okay, thank
Yeah.
Yeah, sorry, sir. I think the error on your code is on the function of the accuracy, where you define pi, and then in the Y prediction, you should bring back the pi.
Thank you. Thank you. So it's picking up P from the original data. It's picking up P from here. That's why.
I'm getting some of those.
Yeah, this is better actually. You see? Very poor and kept going up. But still the parameter is not, oh, they are good, right? Maybe
Yeah,
not.
just running a few iterations. If you run more iterations, I think.
If I run a few more iterations, I should get there. Maybe put 100.
It's fair enough.
Yeah, not bad. So you guys need to keep experimenting and see how you can arrive to the actual value. So I appreciate that. So I forgot this for sure. So it's hitting 99.
So on my side, I've tried using 200,000 iterations.
Yeah.
It's going until 99 and then it's going back down again at the last stage.
Yeah, and that I think that's overfitting.
Oh, okay.
Is the overfitting issue. You can see it hit one and then it started going back.
Okay.
Yeah. Okay. Any other question? So you guys go experiment more. There are more things you can learn. And then come back with questions next week about multiclass linear
you. Sir, can you
regression.
please share again your screen on the part of the accuracy?
What is it?
Can you share your screen on the function, the accuracy function?
Oh, okay.
One more time. Sorry about that.
No, you're fine. It's right here.
It looks similar to what I have, but my accuracy are very poor and they are going down as
Okay, can you share your screen?
accuracy.
Oh, 38.9, that's too much.
I
You
think
should be
it's a
0.1. Let's see your accuracy.
I think I saw a problem there.
What is the problem?
The prediction function is returning sigmoid, not softmax.
Oh yeah, Abdul. The
Where is it?
P prediction function on top of that cell. On top of that
Oh,
cell. Yeah, that should
oh,
should be
sorry.
sorted. And why is still high? Let's see. That's it should range between 0 and 1. Let's go to the max. Prediction accuracy.
Also, I don't know. There's 100 there, like when you're doing the accuracy.
Oh, yeah.
Yeah,
That's fine, but for you, it should be 100 then.
Oh,
it's just making this to be 40%. Okay.
Can you let me see the iteration. You start in 36 and then what?
And then 40, and then it's not going up. 38, 40, and then it's not going up.
Keep going. Okay,
Like it has converged at 40.4.
at 40, okay. Yeah, it could be you need to look at your initial value. You need to look at your what is the learning rate. If you adjust those, because I don't see any problem so far. If you change those, maybe may change. And also you may need to check your data. Are you creating similar to what we have? No, it should be upstairs.
Maybe if you try to on the accuracy function, on the if you change the I see you have P equals to P prediction. Maybe if you could use something else.
No,
Like
it's fine. It's fine on this side. So,
because earlier we defined P as softmax of logis maybe. So just check.
what about the key? Like the first key, we had 24 instead of that. I don't know.
Yeah, that's what I'm saying. The way he's generating those and the running rate, it could have a different implication. Yeah. So yeah, Philip, send yours to him and he can cross check and see what is the problem or which line of a code is different.
okay, thank you.
Yeah, because I don't. Let me see the way you generated your data. Philip, can you check, are those numbers predict 0, predict 1, predict 2 the same as yours? Because that can make the final output to be different. Are they the same?
The equations are different.
Yeah.
Yep,
The
that's
equations
one
are
of the
different.
reason, Abdul.
Can I see a quick question?
It doesn't matter really, Abdul, because I'll put here on a chart. Because those are simulated data. We wanted to show you the we wanted to generate some data following what multinomial distribution. So it doesn't matter really. You can. So those are the one that I have, but yeah. Anyway, I will stop there. If you have any question, feel free to reach out and ask. But I'm strongly encouraging you guys to experiment more, right? You can see those errors are coming here and there. So how do you debug them? You will be able to do that if you have experience, you have practice, you have experience on fitting those regression models. All right, I will meet you next week, and I will design a very simple project that you guys will have to use some concept beyond what we learned here and calibrate an equation. And yeah, maybe you guys can use 2-3 weeks to do that. But anyway, yeah, I'll see you next week then. Have a great week.
Thank you.
Thank you. Thank you.
All right.
Thank you, sir.
Okay,
Thank
bye.